Hi everyone, this is Miss Lasar, and today I'm going to be teaching you about watersheds. You'll be taking notes during this lecture video. Let me show you how. Your notes will look something like this. They're in outline format. They've all been pre-formatted for you so that when you write them down, they're going to show up with sections, details within those sections, details within details, etc. One thing you want to make sure of is that your numbers and letters are vertically aligned. All of your capital letters should all be vertically aligned. All your numbers vertically aligned, lowercase letters vertically aligned, and Roman numerals vertically aligned. To do that, make sure you've paid attention to how much you've tabbed in, one space, two spaces, etc. Things that are in blue, like these instructions, are interesting facts or directions that are optional to write down. Things that are in black, those are your notes. You should write them all down in your notebook. But what happens if I go too fast? Well, remember to pause the video to write down notes when you need to. I'm definitely going to go too fast for you to write down everything as I say it, so pause the video and give yourself some time to write it down. Here we go. First section, section capital A, is watersheds, which is a familiar term to you. Detail 1, what is a watershed? Well, a watershed is the area of land that drains into a body of water. Let me show you an example of a watershed. Here is the Mississippi River watershed. It's this huge area of the United States. It's actually one of the biggest watersheds in the world. And it's all of this land that will eventually drain into creeks and then streams and then rivers and eventually into the large Mississippi River, which then finally drains into the Gulf of Mexico. But here's another example of a watershed. These are 3 watersheds that are all draining water into them separately because of these mountains that are separating them. So when rain falls, water on this side of the mountain range flows into watershed A, water on this right side of the mountain range flows into watershed B. All 3 of these may end up being part of the same larger body of water when they meet by draining into, say, the ocean. And then we would consider them part of that ocean's watershed. But right now, they're 3 separate watersheds divided by mountains. There's other places that water can go. So notice we're still in section A. You don't need to rewrite that. But now we're looking at detail 2 under section A, runoff. Runoff is the water that flows over the surface of the ground before reaching a large body of water. You can see runoff in this picture flowing over the asphalt. It can't sink into the asphalt, so it just flows over the surface. And we know that this is going to drain into a storm drain and then into a creek and then into a river, etc. There's another place for the water to go. It can sink in. Detail 3, infiltration. The alternative to runoff is infiltration. This is water that seeps into the ground. The rainwater that flows over these grassy areas, some of it might be able to sink into the soil instead of flowing over the surface. Final detail in this section, detail 4, are local watersheds. We are part of 2 watersheds, the Potomac River watershed and the Chesapeake Bay watershed, because we, living here in the Bethesda, Chevy Chase, Silver Spring area, have surface water that flows into Rock Creek, which flows into the Potomac River. That makes us part of the Potomac River watershed. And that Potomac River flows into the Chesapeake Bay, so we're also part of the Chesapeake Bay watershed. This map shows you the whole Potomac River watershed. All of this land drains into the Potomac River, and the Chesapeake Bay watershed is actually much larger than this and includes multiple states. Everything that happens on our land flows into the Potomac River and then the Chesapeake Bay. Runoff from streets, gardens, farms, and cities flows over the ground through small streams until it reaches the river and bay. Let's think about that a little more. Notice this is in blue, so you don't need to write it down. You just need to listen and think. So to envision that process, runoff from streets, gardens, and farms enters storm drains, which empty into local creeks and streams, which flow into the Potomac River, which flows into the Chesapeake Bay. So you might be thinking already, what besides water could be in that runoff? And we've already talked about one of these things, salt. But what else could be in that water? Motor oil and gas from the streets, fertilizer from farms or gardens, pesticides from farms, spilled chemicals from roadways or factories, paints and construction chemicals from construction sites or home projects, and sediment Dirt can wash off into runoff. So now we're going to talk about a couple of these pollutants, the three major ones, and their impacts on the environment. Section B, make sure this capital B is vertically aligned with the capital A, types of watershed pollution. First type, salt pollution. First detail about salt pollution, lowercase a. The reason for salt pollution is roads are salted during the winter. And you learned about this in class. We put down salt on our roads. You've seen this. And this is really important because road salt can reduce accidents by over 80%. So we're not going to stop using it. But we could work on decreasing how much salt we use and using it more effectively. Right now, about 20 million tons of road salt are spread on US roads every year. So let's talk about the impacts of that salt pollution. Notice we're still in the salt pollution category. No need to rewrite this. But now we've got detail lowercase b, the impacts of salt pollution. Detail 1, degradation of nearby plant life. These are conifer trees, evergreen trees, by a road that have been covered in salt spray by cars on the road. Notice that they're turning orange and yellow. They should never turn orange and yellow. They're not a deciduous tree, but they've been damaged and hurt by the salt spray. Detail 2, salt-contaminated soil harms soil microbes and plants. They can't survive in salty soil. Detail 3, salt-contaminated water kills aquatic plant and animal life. They also can't survive in salty water if they're a freshwater organism. And detail 4, salt-contaminated streams harm land animals who drink from them. Just like you can't survive on salty water, neither can a moose or a deer or a fox. In fact, some land animals actually like the taste of salt so much that they will drink a lot of salty water until they become dehydrated and die, or they'll wander into roadways to lick off salt, and then they'll turn into roadkill. If you're wondering how the salt in water or soil kills these organisms, great question. That's the topic for next week. Still in our lowercase b impacts section, 2 more impacts. Impact 5, degradation of infrastructure. Salt is really corrosive. This is metal that's been corroded by salt, and this is a concrete sidewalk that's been corroded by salt. And finally, detail 6, contamination of human drinking water, like you learned about in class. The next type of pollution that we'll talk about in section capital B is number 2, nutrient pollution. Make sure this 2 is vertically aligned with the 1 that said salt pollution higher up. Detail A, what's the reason for nutrient pollution? Well, nutrients, specifically nutrients in fertilizer, are applied to yards and farmland. And maybe you've used this. This is Miracle Grow that you might use at your house, a larger bag of fertilizer that could be used on a lawn, and finally, a fertilizer sprayer that's being used on this industrial farm. More than 21 million tons of fertilizer are used in the US every year. So we use a ton of fertilizer, which is just straight nutrients to help plants grow. So what are the impacts of that? Well, section lowercase b, the impacts. The number 1 impact of nutrient pollution is eutrophication. This is a vocabulary word. Underline it so it stands out. Eutrophication means the creation of oxygen-free dead zones from excess nutrients. So we start with excess nutrients. We end with oxygen-free dead zones, which sounds really dramatic. It is. What are the steps that get us there? We're going to have details coming down from this section, from this lowercase b, going through the steps of eutrophication. Watch how this is set up. So now I've just highlighted lowercase b impacts eutrophication. No need to rewrite this. But now tabbed in to the right under that, we've got some more Roman numerals. Step 1 in eutrophication, excess nutrients flow into surface water. For example, we've got this runoff coming from a farm. Maybe fertilizer was just put down. There's all this fertilizer, all those nutrients in this water that's flowing off into a creek. Step 2, algae populations boom as they use the nutrients and cover the surface of the water. These are all algae blooms. Maybe you've seen something like this before. Algae is a microscopic plant that lives in the water, and as it uses those nutrients, its populations explode until we get a massive visible algae bloom. Step 3, light can't get through the algae mat. Look how opaque this is. You can't see through it. That means that light can't get through it. That's going to kill a whole group of organisms. Who's going to die from not having enough light? Step 4, underwater plants die. Because what do plants need? Light. So when these plants are covered up by a thick algae mat and they're deprived of light, they're going to die. This is a bed of underwater grasses that are actually really important to the health of many coastal ecosystems. That brings us to step 5. Bacteria eat the dead plants and use up oxygen in the process. So 2 things are happening here. The bacteria are eating the dead plants, but to eat the dead plants, they actually need to use oxygen. So they're going to be sucking oxygen out of the water as well, which brings us to step 6. Oxygen levels fall so low that underwater animals die because animals need oxygen to survive. So watch this process over time. Here's a little graph. You can write it down on your paper if you'd like to, but you don't have to. This is dissolved oxygen, so oxygen in the water over time. At the beginning, our oxygen is high, and then our excess nutrients are added, and oxygen stays high until the plants die because the algae covered the surface. Those plants lost light, and so they all start dying. And once the bacteria start eating the plants, that's going to start using up oxygen from the water. Oxygen falls until it gets so low that underwater animals die because they suffocate. They don't have enough oxygen. At that point, oxygen is going to keep falling because step 7, bacteria will eat more dead stuff, the dead animals, and they'll use up even more oxygen. Until step 8, an oxygen-free dead zone forms. That's when we've run out of oxygen in the water. Now nothing can survive there at all. Let me show you an example. Mississippi River watershed, here it is, covers a ton of farmland. There's a lot of fertilizer that gets washed into these waterways, concentrated in the Mississippi River, and then dumped into the Gulf of Mexico right here. So what do we see in the Gulf of Mexico? Every spring, after the fertilizer is washed off in heavy rains, we see a massive oxygen-free dead zone forming in the Gulf of Mexico. How big is this? Well, this is the state of Louisiana. So this dead zone is larger than the state of Louisiana. But it's temporary because dead zones can recover. Oxygen can come back slowly. If you've already drawn this graph on your paper, you're welcome to add on to it. You're welcome to draw it now, or you're welcome to leave it off. This graph is optional to draw on your paper. Here's what it would look like as we watch the dissolved oxygen returning to the water. It's going to happen really slowly. Oxygen will return slower than it was used up. And it's going to return as oxygen dissolves in from the air into the water, and waves mix that water around, and the water flows and pulls more oxygen into it. Our third type of pollution that we're going to focus on is sediment pollution. So we're back in capital B. Number 3, sediment pollution. Make sure this 3 is vertically aligned with the 1 and 2, salt pollution and nutrient pollution. Now we're on sediment pollution. Detail A, the reason: any exposed soil can be washed away. Here we've got 3 sites with a lot of exposed soil: a mine, a construction site, and a farm. Sediment, soil, and dirt are all the same thing. We're looking at that cloudy, brown stuff that can be washed away when it rains. So what are the impacts? Well, first, let me just help you envision this. You can see a farm where there's a lot of soil being washed off. There's probably also fertilizer in the soil, but you can see how brown the water is. There's a lot of soil and sediment dissolved in it. Here you can see storm water that's full of sediment being dumped into a local stream. You can see how bluish, greenish, and clear the water was, and how cloudy this sediment-filled water is. Light can get through this water, light cannot get through this water. So now let's think about the impacts. Detail little b, impacts. Number 1, decreased underwater photosynthesis. Plants can't get as much light if they're in cloudy water, and they won't grow as much. Detail 2, creek bed nooks and crannies are smothered. There's a lot of animals that make their habitats in all of the nooks and crannies on creek beds, like you can see in between all of these rocks. They're covered in a layer of sediment. Those habitats aren't there anymore. And finally, aquatic animals' gills are irritated. Just like your lungs are irritated from breathing in smoke, aquatic animals' gills will be irritated from pulling in sediment, and it can lead to death or just lack of growth and ability to thrive. Our next section is about how we use the land and how it impacts the watershed. Section C, land use impacts on watershed. What we do on land matters. Detail 1, impervious surfaces lead to more runoff and less infiltration. Water will flow over impervious surfaces. That's what impervious means. It means water cannot sink into it. Your raincoat would be a really good impervious surface. Your cotton shirt would be pervious. Water can sink into it. Here are two cities. They're different sizes, but these satellite images give us some really good information about pervious and impervious surfaces. Here's Los Angeles. You can see how gray it is. That's all gray asphalt and pavement and cement that's impervious. Water will flow over it. Here's Bethesda. You see a lot more green spaces that include dirt and gravel and grass. Water can sink into all of those areas. So think about which city would experience more runoff and which city would experience more infiltration. Los Angeles will definitely experience more runoff in a major rainstorm, and Bethesda will have more infiltration. Detail 2, urbanization will lead to more salt being used during the winter. Where people live, we put down more salt. We put it down on sidewalks, we put it down on roadways to prevent accidents. It's a public safety choice. Detail 3, landscaping will lead to less infiltration and more runoff. This might be surprising. So what I'm not contrasting here is grass versus cement. I'm contrasting grass in a landscaped area versus a natural area. Landscaped areas have plants with shallow roots, which means that the soil is going to be more compacted. It'll be harder. It'll have fewer air spaces in it, and there will be less infiltration. Think of this as a really compressed sponge. If the sponge is so squashed down, it can't soak up a lot of water. On the other hand, look at a natural space. This will have native plants with deeper roots. The soil will be less compacted. There will be more air spaces, and you'll have more infiltration here. This is a fully expanded sponge that's able to absorb and hold a whole lot more water. Detail 4, agriculture leads to more nutrient pollution, because where there's agriculture, we're putting down fertilizer, and when that fertilizer washes off, that causes nutrient pollution. Detail 5, agriculture, construction, and any exposed soil will lead to more sediment pollution as that soil is washed off and takes all those sediment particles with it. So, Section D, what are the impacts of poorly managed watersheds, areas with a lot of impervious surfaces, only landscaping, few native spaces, few natural spaces? Well, you've seen one of the impacts. This is Rock Creek Park. Just a couple days ago during Hurricane Ida, number one impact is flooding. And that's because all of the water is washed to one place, in this case, Rock Creek, which you can see right here. And so while most areas of Montgomery County didn't flood, areas right around Rock Creek that absorbed all of the stormwater did flood. Impact number 2, erosion. That stormwater, as it gets higher and higher, is really powerful, and it can wash away stream banks. It can rip the roots out of trees and cause them to topple. It's a really powerful force. And impact number 3, contamination of drinking water, like you saw in class. As salt is washed off of roads, flows into our drinking water sources, we can end up with water that's potentially too salty to drink. So what are the solutions? Here's our final section. Section E, solutions. The whole purpose of these solutions is to slow down the water, prevent it from becoming runoff. Solution 1, a rain barrel. That's a structure that looks like this. If you've looked at the side of a building, you've seen downspouts that are shuttling water away from the building, usually directly into a storm drain. So this is not slowing down the water. This is pumping it directly into a storm drain, unless you put a rain barrel in the way. Here, this is a barrel that's collecting all of the stormwater and it's storing it. You can save this water and you can use it to water your garden, and only when the rain barrel overflows will it get dumped into the storm drain. Another solution is a rain garden. Here, we've got a downspout that pumps water not into a storm drain, but into a garden full of deep-rooted native plants. That spongy soil will absorb a lot of water and less will run off into the streets and into storm drains. Solution 3, pervious surfaces. That's the opposite of impervious surfaces. These are surfaces that can absorb water and allow it to infiltrate. Pervious pavers have gravel in between them so that water can flow down through the gaps between the tiles. Porous asphalt is a pretty new invention. It's still really expensive, so you don't see it in a lot of places, but it's asphalt that can actually absorb water and where it won't just flow over the surface. You can also replace paved surfaces with gravel, with dirt, with grass. For example, this driveway covered in gravel instead of covered in cement or asphalt. And our final set of solutions are larger scale. Our fourth solution is a buffer strip. This is a planted area along a stream or creek or stormwater flow area that's planted with native plants. It's not mowed, it's not landscaped, and stormwater will run over it and be allowed to infiltrate before it gets to that creek. So hopefully this will filter out some of the sediment, filter out some of the nutrients, and absorb some of the water before it gets to the creek. Fifth solution, reforestation. Add more trees, add more native plants, replant natural areas. The more plants you have, the more natural areas you have, the deeper the roots will be, the more infiltration, the less runoff. And finally, wetland restoration. Wetlands are areas of grasses and other water-loving plants that are on the edges of waterways. And by having intact wetlands, those plants will be able to absorb a lot of sediment, a lot of nutrients, even salt before it reaches the larger waterways, and it'll protect those waterways. So here are some of the solutions to the problem of watershed pollution. You've learned about watershed pollution, you've learned about land use and how that impacts watershed pollution, and you've learned about some solutions to the issues of watershed pollution. If you missed some notes, rewind the video and rewatch those sections. I hope you enjoyed this lecture, and we'll see you in class.